Hey everybody. I just gonna finalize two-dimensional motion. It's gonna, just because I'm really bad at video clips and trying to get them all unified, I'm gonna try to do some calculations as far as initial velocity for my projectile launcher, and then I'll do a second calculation for predicting the landing zone. So ultimately, from our last lesson, horizontal motion was a constant velocity scenario where we had velocity equals change in position over time. There was no net force as the object moves horizontally. Now there might be some wind resistance, but we're going to call it negligible. And it really turned out negligible on the video. So cool, cool, cool. And that was a tennis ball outdoor. Vertical motion, it's subject to the force of gravity, so there's going to be constant acceleration, and it's going to oppose its motion. So the constant acceleration equations, these three equations, can help us predict initial velocities and or how high something goes, or if I know the initial velocity, well, I can figure out how high it goes or how long it's going to stay in the air, like hang time. Okay. One of my videos that we played a while ago was the world record for the blob, right? Which I think is super fun. So much about this has so much physics in it. For instance, the three people jumping, that's got a ton of potential energy. The blob has spring potential energy that results in the dude's kinetic energy taking off, which transfers to potential energy, etc. So they're trying to launch him, right? Now, the coolest part for a physics teacher is to watch this stop motion or this picture where they compile his position every second through his flight, okay? So knowing that he's 17 meters tall, I could calculate how fast he took off, okay? This is cool. Watch his flight. What's that shape? A parabola, okay? I think that, honestly, I'm geeking out here. The flight of a tennis ball shows up like a parabola. The flight of a dude getting launched from a blob is a parabola, right? As long as there's not much influence on the object itself from wind resistance, okay? Now, I have a projectile launcher, and you probably have seen those before. I basically recorded it being launched. Now, I didn't launch the full height. There are two ways. Basically, what I want to do is I want to calculate the initial velocity of that launcher. And there's two ways I can do it. I can measure out how high it goes and use potential energy and kinetic energy. Or I can use my constant acceleration equations, okay? So I'm going to get some data here. As it goes through, I'm going to try to find where that ball takes off. Right, and it's going to be a blur. There it is. Did you see it coming out of there? And that's at about 5.69, so 5.7 seconds. It's when it takes off. And then I'm going to try to find when it comes down. It's going to be another blur, and it's close to 7 because I've seen this. 6.9. Ooh, there it is. So the bottom of the ball is right around there at 7 seconds. I'm going to go back a frame. Do I see it? Ooh, I don't even see it. Ooh, there it is. It's changing right at 7. So when it got down here, it was about 7.0. Right here, it's about 6.9. So I'm going to say, well, it's really weird to do this, but I'm going to go 6.95 seconds. Okay, and I'm going to show you how to calculate the initial velocity of the launcher. And we can take this to our two-dimensional motion. Okay, so let me just calculate this. So let me get my calculator. My time in the air was 6.95 minus 5 let's just call it 69 since we're in 3 digits. That's 1.26 seconds. Equals 1.26 seconds in the air. Okay. My acceleration due to gravity right, is this negative 10 meters per second squared. Now, there's a principle of flight. The initial velocity, and that has to do with energy, right, gets to a certain height, and from that certain height, I get a certain velocity. So I know my final velocity, my initial velocity, is going to be equal to my final velocity, unless there's a net force, which there really isn't a big net force on this. It was in my back shed, and if a tennis ball can look like a parabola with no forces acting as far as wind resistance, in my shed that has no wind resistance or wind blowing, we're good to go. So I'm going to use, if I'm going to try to find out my initial velocity, I'm going to use this equation because these two are the same, okay? So I've got V equals V, right, plus the negative 10 times 1.26. So how does, oh, and also, right, this direction is down. Okay, sorry, I almost forgot that. So how do I work this out? I've got 2V, right, equals a negative, what do we have? A negative, right, 10, oh, oops, that's not hard, 12.6, okay? V, my initial velocity, is going to be 6.3 meters per second. Now I know I have a negative there, but that's fine. So ultimately I've got a magnitude of 6.3 meters per second coming out of that launcher, which is actually pretty good. So I'm going to take this value, okay? I'm going to take this value and I'm going to apply it to this scenario, okay? And I'm going to use a prediction, okay? I'm going to try to predict the landing zone at a 45-degree launch. Remember, that was the maximum launch angle, right? Maximum launch angle. So what do I have to do? And I'm going to do this calculation at a different time. What I need to do is I need to find the influence of this velocity. This velocity has a magnitude and a direction. So there's a certain amount of vertical velocity and there's a certain amount of horizontal velocity. And how do we find that? We find it using trig, okay? So in this scenario, Vx, right, that's Vx is the side, and I know the hypotenuse, 6.3, I can find this using trigonometry, and I'm going to show that trig on the next video. The important part of this video was finding the initial velocity of that launcher so I can use that to predict its landing zone. Okay? I might change this angle because this is 45 and that would be 45. Maybe I'll change it to 60 and 30 so I can show you the trig for that. All right? Next video is going to be calculating that landing zone, and then I'm going to see did I do it right? Okay? All right, next video.